Hello everyone, I hope you're enjoying the Fall 2020 MassBay STEM Expo. My name is Joe Remondi and I'm a mechanical engineering student at MassBay. Thank you for attending our expo and thank you for taking the time to look at my project, Cycloids and Related Problems, that I've completed for Calculus 3. This is just going to be a short video summary of the project. The link to the entire project can be found in the project description. So what is a cycloid? A cycloid is the curve that can be represented by tracing the path that a point on a circle takes as the circle rolls along a fixed path. Imagine that the wheel here is a wheel, the circle here is a wheel rolling along a flat surface represented by the horizontal axis. The cycloid curve is what we see up here in red. It is the curve traced by point P as the circle rolls. So the first goal was to find the equation to determine the x and y values of point P as the circle rotates. The curve is going to be defined by two values, the radius of the circle and the degree of rotation. The degree of rotation is going to be given in theta. We will continue using the circle of radius 1 for the simplicity of our calculations. So here it is in its initial position. So here's what we're trying to find. We're trying to find this function in terms of theta and r that will give us the x and y coordinates. We can see from our initial position here, the function of 0 rotation and a 1 radius will put us right at 0, 0. So the desired xy coordinates are those of point P above. Here we see the same circle of radius 1 having undergone a rotation of pi over 3, equal to 1/6 of a total rotation. We can see that x is roughly 0.2 looking at the graph and y is roughly 0.5, but we can figure those out exactly with trigonometry. See this x coordinate, the difference between the x coordinate of AP is going to be AB minus QP, easy enough to find with trigonometry using the sine function. And then for the y, we know that the y position is going to be CB minus CQ, or BQ. And that'll give us r times 1 minus the cosine of theta, as that side of the parametric equation. So here's some applications of the cycloid parametric equations. We can do the arc length. So we see the cycloid after it's undergone, half of a rotation, or pi radians. So those will be our limits of integration eventually. So we'll look at this arc length function and see how it requires the derivatives of the x and y functions. Let's go ahead and find those. And when we do, just notice that the derivative of the x function is actually identical to the y function, which will come up later. So to resolve this interior term, we sort of just factor this out and apply the half angle identity here is sort of the key to simplifying this. And note that that'll mean that in the end, when we do our limits of integration, we're going to be integrating from pi over 2 to 0 rather than pi to 0 because we have this half angle identity in here. But again, if you wonder any more about this, just take a look at the full project because there's more in-depth explanations there. So let's look at another problem, what's called the Todachrone problem, from Toda meaning same, and chrone meaning time. And this seeks to define a curve for which any object moving down it will reach the bottom in the same amount of time regardless of where it starts from. So you can see in this little animation I created here that even though point A travels a much greater distance than point E, it takes the same amount of time for A to go from the top to 0 as it does from point E to go from just next to 0 to 0. So we're going to try and how this worked was essentially that it was suspected that this curve was a cycloid. So we're going to go ahead and plug in what we know about a cycloid and see if it holds true. So the velocity of this object is going to be able to be found as a function of the y coordinate using conservation of energy. 1/2 of mv squared is going to be equal to mgy. And g is just going to be a constant, 9.81, but we're just going to leave it as g. So we previously had this arc length. So what we'd like to do is substitute, we know ds is the arc length, so we'd like to substitute what we've already found for arc length in there, and we end up with this here. The time is going to be equal to the integral from 0 to pi of r times this value divided by this. You can see the top and bottom here both have a square root of 2 minus 2 cos t, so we can pull that out of there, and it turns out that the final term doesn't even have any t in it, so it's going to be independent of time. We see that the amount of time it's going to take to get to the bottom of the ramp is just going to be the square root of the radius over gravity. It's going to remain constant as long as, so anywhere from between negative pi, and as long as the lower limit of integration is 0, meaning we're measuring the amount of time it takes to get to the very bottom, then this will remain true. So here's another problem, the brachistochrone problem, from the Greek brachisto, meaning shortest, and chrone, meaning time. So this is the curve for which an object moving down it, affected by gravity, will reach a point at a lower elevation in the fastest time. So essentially, what of these curves would get an object from point A to point B the fastest? Intuitively, we know that the short line is the shortest distance, but it doesn't end up being the fastest way to get from point A to point B. So we're going to apply a form of the Euler-Lagrange equation to try and determine this function that will be corresponding to a desired minimum, which in our case is going to be time. So it starts similar to the Todochrone problem, where we know that 1/2 of mv squared is going to equal mgy by the conservation of energy. And then again, we're going to compare the arc length to the velocity of the object moving. So we'll take our original arc length formula here, and we'll just pull this dx out of it because we'll need it later when we're integrating. So we end up with this function here. And because this function is in the form of, essentially because the derivative of the x function was the y function, means that our points are in the form of y comma y prime, essentially. Meaning that the derivative of the second point is, that the second point is a derivative of the first point. So they're related in that way. A lot of times you'd have, if you had completely unrelated values, you'd just, you'd have to apply the full Euler-Lagrange equation. But we can apply this and set it equal to this constant c. The c will end up getting altered, so it's not a big deal. It'll just remain a constant. So if you'd like to see how I work through all this, you can just take a look at the full project that I posted in the project description, because there's a good explanation of how I arrived at this. But essentially, we're just going to square both sides. So you end up with this 2g and then multiplied through by this 2g. And then when we flip everything over, we end up with this equation here, y times 1 plus y prime squared is going to be equal to this new constant, which we'll call k. So here's the proof of how that term ends up equaling a cycloid. It was a little bit of a jump from here. I definitely recommend that if you're interested, you do take a look at the my full project. But it's pretty amazing to think of how some of the older mathematicians did solve this without variational calculus. So if you have any interest in that, I definitely recommend learning a little bit more of this. And if you go through my project, there's some great sources at the end that you can check out to learn a little bit more. So thank you for taking the time to join me on this exploration of the cycloid curves and some problems related to them. I really enjoyed doing this project, and I learned a lot doing it. So thanks again for viewing this and some of my classmates' projects. I've never done anything quite like this, so I'd like to know if I did communicate the information in an effective way. So I value all of your feedback. Please have a nice day, and we'll see you soon. One additional thing I'd like to share with you are some of the sources I used in creating this project. We have both textbooks I used in this class, and then some great articles I found online relating to the brachistochrone or the Todochrone, or simply just to the cycloid. But if you are interested to learn any more, I would advise definitely checking out some of these links or looking up some of these resources, because there's a lot of information out there. Again, thanks for having a look at my project.